Hello, I'm Catherine Starcher, and this is Lab 4 Circuits. The goal of this lab was to compare predictions and measurements for the behaviors of DC and RC circuits. The two important physics principles to complete this lab were energy conservation, which is seen through the loop rule, and current conservation, which is carried out through the node rule. Ultimately, I found that my predictions for current values match the measured values from the ammeter in the program, which were both 0.02 amps. And in part 2, the predictions for the RC circuit were very close to measured values in the program, which shows its accuracy. In part 1, using the loop rule, I predicted that both I1 and I2 would be 0.02 amps. And I knew that I1 would be equal to I2 because of the node rule, which says that current is conserved, so current in must be equal to current out, and I1 would therefore be equal to I2. The measured values were also both 0.02 amps on the ammeters. In the diagram on the right, you can see the potential differences on each of the segments of the circuit diagram. So you can see that both of the batteries collectively have a potential difference of negative 3 volts because they're 1.5 each. And then there is no potential difference until a resistor is reached, and both of the resistors have a positive potential difference. So I knew that the sum of all of the potential differences would be equal to 0 because of the loop rule. In this slide, you can see a diagram that shows the change in potential difference across each of the different segments. And so you can see that it jumps from 0 to 1.5 and then to 3 volts across each of those batteries. And then it stays at 0 across the straight wire. And then at each of the resistors, it decreases until it ultimately reaches 0 again. I was also able to predict the resistance across each of those bulbs using calculation. And so in order to do that, you divide the potential difference value by the current, which should give you the resistance, which for the first resistor, which I knew to be 47 ohms, I got 47.95 ohms. And for the second resistor, which was supposed to be 100 ohms, I got 102.05 ohms. So with these calculations, you can see that there's a bit of a difference between what the program predicts and what calculations also predict. In part 2, I found that the time in order to charge the capacitor with a 10 ohm resistor bulb was 6.04 seconds, and the time to discharge was almost 13 seconds. When the resistance was increased to 20 ohms in the bulb, I saw roughly a double in the time that it took to charge the capacitor and the time it took to discharge the capacitor. So this just shows how increasing resistance increases the time it takes a capacitor to fully charge. Finally, we constructed another RC circuit with a 9-volt battery, a 200 millifarad capacitor, and a 30 ohm light bulb. Using energy conservation for RC circuits and rearranging the equations seen on this slide, we were able to find RC, the time constant of the circuit. The slope of the graph on the right side of the screen is equal to negative t over RC. And so we took the negative inverse of that in order to find t, the time constant. This time constant is the time at which the voltage difference has dropped to 1 over e of its original value. And we expected it to be the value 30 ohms times 0.2 faradays of 6 seconds, but in the experiment it was measured to be 5.998 seconds, which is very close to the expected value. If this lab had been done in real life, a real ammeter would have natural resistance causing the current to be slower, whereas in this simulation we can have sort of a perfect world scenario where the ammeter doesn't add any resistance to the circuit. And if our ideal model of a battery but no resistor in a circuit were to exist, a capacitor would become charged instantly because there would be no resistance to slow it down, but this would not happen in real life as it's impossible to have no resistance at all. Thank you.